Hello, I think we should get started. We're a few minutes behind schedule, but it should be okay. This talk is called Secure My Socks, and hopefully it's going to be a little bit fun. It's aimed towards developers mainly, and it's kind of at like an intermediate-y kind of level. What I'm going to be doing is talking about microservice security and walking you through some aspects of microservice security. I can't take you through everything because it'll take too long. So I'm going to be concentrating on container security and a little bit of security in the orchestrator as well. So it does require a little bit of prior knowledge, a little bit of Docker knowledge and a little bit of understanding about what Kubernetes is. But if you don't, that's kind of okay. You should be able to just about follow. So my name is Phil Winder. I have a small consultancy in Yorkshire called Winder Research, and I mainly work in cloud native and data science. But I'd like to thank these guys at the top, Container Solutions and Weaveworks, because Weaveworks are the people that sponsored this talk. This is some work for them, and Container Solutions I partner with quite a lot. So good to get them mentioned. So the first thing I do, let's get into the presentation slowly. The first thing I do is always Google the presentation name. I've searched for Secure My Socks on the internet because I want to make sure I'm not duplicating anybody else's presentation. And the first hit is this company called Socklocks.com. And I didn't know this was a thing until I found this website. Apparently, people are quite worried about it's perfect for keeping similar color, but not exactly matching socks separate. So if you have that problem, the difference between black socks and very, 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 very dark blue socks, I'm not that bothered, if I get them mixed up in the wash. But if you are, check them out. Hilarious. I just had to add that in. But yeah, let's be a little bit more serious. And one of the main things that I hear as a consultant is a lot of people and companies are concerned with PCI compliance. So I think PCI compliance is quite a good place to start because it provides a bit of context of why you would want to do security. So PCI compliance, if you're not aware, is payment card information compliance. I think that's what it stands for. It's involved with the idea of protecting users' data. And effectively, it's a bureaucratic process that you have to go through to ensure that you can handle a person's financial information. And the way that most companies deal with this is it kind of comes down to two things, really. It comes down to the developers, because the developers are the ones that have the access to this information. And basically, do you or do you not trust the developer? For most large enterprises, it's a lot easier to just assume trust on behalf of the developer. So this means that developers don't really have to worry about too much authentication in their and access control stuff within their application. They can assume that everybody's going to do the right thing, and then they employ massive teams of auditors to consistently and continuously audit their application to make sure that some people don't access information that they're not supposed to do. So generally, yeah, this audit team then goes to the governing bodies, and they're the ones that prove to the governing bodies that they can audit their system effectively enough to make sure that no sensitive data is being leaked. And that's fine for enterprises and huge companies. But for anybody that's an individual or anybody that is a small to medium-sized business, we can't afford this audit. It's just too expensive to continuously do it all the time. So how do we fix that? So one of the easiest way of doing this is by limiting the surface area. So when we're talking about microservices or services or networks or firewalls or anything, if you're limiting the surface area of your thing, then you're providing less access points and less capabilities of accessing the wrong information. I've got a picture there. Yeah, so put simply, if you've got something, let's just imagine that's an API rather than a set of services or something, then if you've got a small API, then you're far less likely to leak information out of the singular API than if you have a large number of services that are all publicly exposed. Yeah. But PCI compliance as a thing doesn't necessarily mean your application is secure. You know, this is just this is only relevant to payment card information, basically. It's not relevant to, you know, if you're worried about being hacked, or if you've got any other sensitive data, then there's all sorts of other reasons why you would want to be secure in the first place. So I like this example. I found it a couple of months ago, but there's a guy that came up on Stack Overflow asking the question, why is Docker swearing at me? And if you read through that, then basically what happened, on this particular version of Docker, when he installed it through Windows and he tried to log in, he typed the wrong password, I think, but the error message for this was incorrect username or password, fuck you. And that was an actual thing. So what happened there, I presume there must have been a disgruntled employee that was about to leave and inserted this bomb in the end of his, in the last line of his code. And there you go. So, you know, Docker is the self-styled, they are microservices as it were. And even the big guys can't get this right all the time. So yeah, it's not easy. Security is actually quite hard. And the reason why it's hard, it's not that it's complex necessarily. It's just that it's like inherently there's no goal. It's a never-ending process. Because you can say that, you know, I have hardened my software, or I've protected myself against certain things, but nobody would ever dare to say that I am hack-proof, because that's just asking for, you know, that's just asking for someone to break your code. So all we can do is iteratively, and when required, start exploring all of the various failure modes that could happen within your security. And that is an ever-increasing list. And it's quite, yeah, it's a long and comprehensive issue that you'll have to go through at some stage, depending on your business requirements. And today, I'm only gonna concentrate on container security and network segmentation and policy. Actually, just at this point, I think it's worth mentioning, when would you do this analysis? When would you add security? So I personally, from like a pragmatic point of view, there's no point having security. There's no point having a secure piece of software if the software doesn't do the job that it's supposed to do. So I think the first and foremost thing that you should do is make a working service or a working tool or whatever it is that you're doing for your business. You always bear security in mind from the start if you can, because it will certainly help you later on. But I don't think, personally, it should be the first priority. It's probably the second priority. So to look at these things, I'm going to use a tool that we created at Weave called the Sock Shop. And it's an open source reference microservices architecture. And the reason why we came up with it was because when we started doing the microservices a couple of years ago, we kind of realized that there was a lot of talk and there were a lot of blogs and there were a fair, you know, the books are coming out slowly and steadily. But there's nothing really that realistic that you can use from the get-go. So we created this as a way of being able to, you know, provide a reference architecture for microservices, but also test it within our applications as well. Because we have a whole range of tools that we need to test with a microservices application, and so we use it for that. But the beauty is that you can go away and you can look at it, and it looks something like this. So oh yeah, and another thing about today, I've actually got quite a large number of demos, more than normal, so please pray to the demo gods that everything's going to work. Okay, so this is the Sock Shop running on our staging infrastructure, on our staging cluster. And you can kind of see, it's basically an e-commerce site that sells socks. And you can click through and add to the cart. And it's kind of vaguely relevant. I hope you like the pictures. These are basically just the engineers' socks that were in the office at the time. Ready for action. Engineers, be ready to smash the next bug. Be ready with these super action sport masterpieces. This particular engineer was chased away from the office with a stick. So yeah, sport socks, like it. And the whole idea really was to try and make it as realistic as possible. So it's supposed to kind of do everything that a real e-commerce site is supposed to do. And we found that by providing a realistic example, you're not stuck with the standard hello world kind of just singular Docker images. You yourself can get this at git.io/sockshop, and that will redirect you to the GitHub website called Microservices Demo. And the coolest thing about it is actually, it's not necessarily the application itself. I think the coolest part is that we've created a series of deployments for various orchestrators. So today I'm going to be using Docker Compose and Kubernetes, but there's also deployments for Mesos and for Nomad and AWS and lots of others as well. So you can kind of use the same application to test out different orchestrators if that's what you're interested in. Okay. So let's get cracking. Container security. So when we talk about, so containers as a thing have their own unique set of security problems. We've got a list here that I'm going to go through: restraint, immutability, provenance, and hardened OS's modules and policies. So the first one, restraint. This is a really key thing. So the container in itself is a fully working operating system. When you install and use your applications inside these containers, depending on how you start that container, it'll not only have access to the container itself, but also potentially to the root file system as well. If it's got access to the root file system, that means it can basically do anything. So restraint is the idea of applying restraint through a various number of ways to your application within that container. So we're going to say, don't run the application as root. We're going to use kernel capabilities, caps, to restrain exactly what that application can do. Immutability is the idea of trying to make your container immutable, surprisingly. And the idea here is that a number of exploits are trying to alter the files within your system to do various things. So for example, if I gained access to your container and it wasn't immutable, then I might be able to read some of your data or deface your website or do something like that. So if we can make it completely immutable, i.e. it's read-only, doesn't change, then that prevents that instantly. Now, provenance is actually an interesting one because that kind of only happens with containers. So when you go onto Docker Hub and download a container and you type in, if you look for a Hello World container and you just pick a random one, when you start that container, you don't actually know what that container is doing. You can't really be sure unless you go and start investigating the code. So this is actually one of the biggest problems for enterprises. They're really worried that they're going to be running code that isn't meant to be used. And so the provenance of that container, where it's come from, who has developed it, and what is running inside it is really important. There's a couple of tools out there now that are automatically scanning for these types of things. Do they have? Can they ensure that the person that created this container, did they actually create this container? Does it contain any exploits and bugs and viruses and stuff like that? And then finally, hardened OSs. So we've got things like SE Linux, which is a hardened Linux kernel out of the box. And modules and policies, so like various, the Debian-based distributions have got things like AppArmor to try and provide extra policies to provide more fine-grained control over who can do what. But for this demo, I'm going to talk a little bit about restraint and immutability. And one of the things that you see all the time, all over the interwebs, is that Docker containers hardly ever set a user. They always just, from this, add my code, run this code. They hardly ever set a user. And this is an example of some crappy code. And I can say it's crappy because it's one that I wrote a few years ago. Here we've just got the standard Alpine node Docker file. Actually, sorry, not standard, but anyway. And then we're just doing some stuff. We're installing some node packages, setting some environmental variables and ports, and then we're running a command at the bottom. No way through that, nowhere in there are we specifying the user that should run this container. So by default, this will run as root inside the container. So let's imagine that we are running that container now. So I just need to disconnect from there. Okay, I'm going to use the Docker Compose deploy from the microservices demo website. Okay, and we've started all the containers there. And when that starts, there we go. Then we should be able to go to localhost. Oh, I've just spoiled the hack there. Oh well. We've got it running on localhost. So now I'm going to exec into the front end container. So I haven't gone into details about the actual structure of the application yet. I'll do that a little bit later. But basically, there's a container right at the front end that's serving the UI and stuff. And so because I haven't specified a user, this user is actually running as root. So I can pretty much do anything I want. So I've just got a little bit of code at the bottom here. And let's make this a little bit bigger. And because I'm root, I can install my own packages. I can install a Bitcoin miner. I can, do anything I want. In this case, I'm going to make a train because trains are cool. Okay, next. We talked about immutability. And the easiest way to ensure immutability is with a read-only file system in the container. If you, so this is part of an insecure Docker Compose file. If you haven't seen this before, it's like a specification to start Docker containers. It's quite simple. This example is just the name of the service that we're going to start. We've got an image that we want to run, host name, and some other stuff. So that's running right now, as you can just see from the previous example. And we're going to, again, because it's not read-only, we can basically rewrite the entire website. So there we go. So this is when you see those examples on the internet where people have been defaced for whatever reason. It's probably because they've not made their file system read-only. So that's, and the worst bit is that's really simple to do. That's like one of the simplest things you could possibly do. And then, so, yeah, and this is and this is where we're starting to figure out how we fix some of these things. And the read-only bit that I'll come on to in a second is probably the easiest part. But what is a little bit more complicated is capabilities. So capabilities is a Linux kernel feature which allows you to specify exactly what an application can or can't do. And they are split into like these fine-grained list of capabilities. So you could have capabilities for writing to the file system or interfacing with the networking stack or, I don't know, a whole load of things. And the reason why they're probably not more popular is because they use quite low-level Linux tools. So you kind of need to know they're there before you can use them. And the problem is nobody really knows where to do these. And the main issue is that sometimes the capabilities belong in the orchestrator and sometimes they belong in the container. So if it's like a container level capability thing, then if it's specific to the application, like the application requires some capability to open a specific port or something, it has to be in the container or else it won't work anywhere. Other things, like all other things that are not necessarily specific to the app, can be restricted by the orchestrator. So it's a little bit confusing where to place these things. So I'm going to actually show you how to do it. So this is the Docker file for the catalog service. So this service hosts some static content, basically, things in the catalog. And again, super simple Docker file. It's a BusyBox Docker file, no user, fantastic, copying the app and then running the port. So what we could do is we need to first add the user. Because if we don't want to run as root, we need to add a user so we can run as someone else. So because we're using BusyBox, and this differs depending on what distribution you're using, but because we're using the BusyBox, we've got these tools called add group and add user already built in, so that's great. So we're going to add a new group, and we're going to add a new user, and then this line here sets the container to use that specific user. So when this application starts, it won't have permission to run as root. If we tried that, however, that would fail, because if we're not root, we can't bind to a privileged port. So a privileged port is any port that's under 1024. So port 80 is privileged, and you need to be root in order to gain access to that automatically. So there's a number of things we could do. We could add a proxy. So we could add a proxy that is running as root and forwards to another port. But that's a bit hacky, maybe involve another container. You've still got something running as root, so there's a bit of a security risk there. We could change the port to a non-privileged port, so 8080 or something like that. But again, I don't think that's ideal either, because this is a web-based, HTTP-based web app. It should really be running on port 80. That's what everyone's expecting. So it really should stick on port 80. So one thing we can do is use these caps, these capabilities in the kernel, to give it the permission to bind to a privileged port. To do this, what I've had to do is actually switch to Alpine. So Alpine is another Linux image, Linux image, and I've used Alpine because it's got a richer tool set out of the box, and it's got a really nice package management system, as opposed to BusyBox, which doesn't have the package management. It's a bit harder to use. So I've switched to Alpine. I've still got the add group and add user stuff, but now I'm adding a library called libcap. And this is the kernel. This is the library that interfaces with all the kernel stuff. Inside this library, you've got a couple of executables. Here, we're using setcap. So setcap is a binary that enables you to set capabilities on binaries. There's another one called setsh, which is kind of like a capabilities-enabled shell. So you could execute a shell script with certain capabilities. So there's a couple of different ways of how you can give the application capabilities. But here, I'm basically assigning the binary to my user that I've just created, and then I'm giving it this capability to bind to a particular port below 1024, and that's the name of the capability there. So if we run that, that would work. So then the next level of things is yes, okay, great, we've given our container the capability of binding to a port, but we haven't really restrained it in any way. It's still got the ability to perform lots of other kernel calls, network stuff, disk stuff, and it doesn't need it. Our application doesn't need it. And this is where you would put the restraining things inside the orchestrator. So this is a Docker Compose file again, and in Docker Compose you can specify the capabilities with the cap drop and cap add settings. So the cap drop has got this special all key, which means you're going to drop all capabilities, every single one of them. And then we can simply use the cap add to re-add back the ones that you need. So in this case, we only need to bind to the service, so we're just going to use that. Here we've also, this is where we're setting the read-only to true. So underneath the container, when the kernel gives us a file system to operate from, when it mounts that file system, it sets it as read-only, so you can't edit it in any way. So when the container starts and you've got read-only set to true, you can't write to it. This is pretty much the same, but for Kubernetes. So again, depending on what orchestrator you're using, it differs how you actually set this. For Kubernetes, it's a little bit more verbose, but it's basically the same settings. We've got a capabilities section here where we're dropping everything and then re-adding a specific capability. And again, we've got a read-only root file system here set to true. It's got another neat little feature, actually, which is really useful, which is an option called run as non-root true. And that will perform a check every time it starts this service. Is this container running as root or not? If it is running as root, it'll just crash it out. It won't start it. So that's a nice enforceable way of checking that you you're really not using root. So the result, let's try our little hack again, but this time we're going to use the secured version of the Docker file and the Docker Compose script. So let's just wait till that's started. Let's see if that's back up and running again. Okay, cool. And I'm going to exec into the front end again, and then try and run my little hacky scripts. And there we go. Don't know if you could. Oh, sorry about that. Let me make it bigger. Right. So what we've done now is we've tried to install our Bitcoin miner / Steam locomotive again. And this time when we try to install it, it says unable to unlock database, permission denied. So we're not root now, so we're not even allowed to install any applications. Now we're trying to write and deface our website. Again, we can't do that anymore because it's a read-only file system. And if you're really interested, you can actually look at the file descriptors that define what capabilities are allowed in this container by grepping inside this file here, and it gives you all of the low-level stuff. And lots of zeros is good. Lots of zeros means you're not allowed anything. But that's why these libraries exist, because you really don't want to interact with this horrible, like low-level binary crap. It's nasty. Okay. So, top tip number 2, or 3, or 2, I can't remember. But when you're writing your Docker containers, set a user, make it read-only if you can, use capabilities. So out of those, the read-only bit is the simplest. It's one line in your orchestrator, it's dead simple. The user is a little bit more tricky, but quite easy depending on your distribution. Capabilities, probably the most complex because you need to. Yeah, and actually this is an interesting point. So one question I get is, how do you figure out what capabilities your application needs? Well, the simplest way of doing it is just denying everything, blocking everything, and then incrementally start adding the things that are required for your application to work. The idea is you want to restrict as much as possible, but your application obviously needs to work. So yeah, best practice is to drop all and then just re-add the ones that you really need. So, interlude. Did you know that in 2003, 12,000 people were hospitalized because of socks? How? What? I don't know. Anyway. So, network segmentation. So we talked about PCI compliance and whether you trust the developer or not. And this is where this really comes into play. Because one of the easiest ways of securing your services from both attack and accidents is by applying certain network policies to restrict the communication between services. So this is actually the structure of the microservices demo architecture. It's got a front end which has got like some static content to host the website, and it's also doubles as like an API gateway as well. Then we've got some back-end services which are doing, traditional parts of the e-commerce business. We've got an orders service which is handling the orders pipeline, and then we've got like a payment gateway or a fake payment gateway, counts-like service, catalog, and a cart, and so on. Each of the circles is a microservice, and then some of these microservices are backed by their own databases. There's a couple of other bits and bobs like queues as well, but we won't be getting into that today. So the first thing that we will want to do is, how do we prevent external access to a container? Because we obviously don't want the public, Joe Public, coming in and accessing a container or a service that they're not meant to access. And as you're probably all fully aware, we would use a firewall, specifically a bigger firewall. And if you can define the de facto trumps firewall, the bigger, better, strongest, best firewall that you can, you're basically applying this on a machine level. And this restricts public access. I think we're all quite used to firewalls now. If you're if you're dealing with your own servers, then you may be dealing with IP tables or something like that. If you're on the cloud, then you're working with security policies. But it's all fairly well-known stuff. But the issue is that if somebody could get access to one of your services when they're not supposed to, like if they got access to the front end, then they would immediately have access to anything else in the system. So I've seen, actually, it's not in this example, but we've got another example where on one particular version of Node.js, there was an exploit where you could pass in a query that would run within Node.js, but have access to everything, to the root file system, to the networking interface, and anything. So from the front end, I could run a special query through the browser, and it would return results from other services or something like that. So this stuff does happen. You don't have to have shell access in order to do damage. You can do it via the browser, depending on any exploits that exist in the browser at that time. And that's the scary bit. What's far more realistic, I think, is this becomes part of an architecture problem. If we've designed our services in this particular way, we've done it for a reason. We don't want the front end to go directly to the shipping service or the delivery service because it has no, it has no reason to do so. And also, it prevents any accidental communication. If you start leaking information by calling APIs that you shouldn't do, you're adding in another coupling point to your application that you don't need. So we need a better, more fine gray of creating firewalls. And one of the easiest ways to do this in microservices land is to create individual networks for groups of services. And this is called network segmentation. So you are segmenting your application into different networks so that certain services can't encroach upon different networks because they're not connected to it. So in this case, the front end wouldn't be able to connect to the shipping service because there's no direct access there. And that's great, and that's works reasonably well, and it's quite simple to do again. So in Docker Compose, it looks something like this. We're simply, in our service definition, we're specifying the networks that this particular service is connected to, and it's connected to back office. So shipping would only be able to connect to different services that are within the back office network. But the problem is it's still not quite fine-grained enough because the catalog, because this was still in the same layer. Oh, actually, I think I've got a picture next. So let's imagine now that the catalog service accidentally communicating with the cart, which could happen because it's in the same network as we saw before. But logically, it shouldn't need to happen. The catalog really has no dependencies on the cart and vice versa, so why is it communicating with each other? We're just adding more complexity and more coupling into our application. So, the network segmentation doesn't quite work there. But what Kubernetes specifically provides is something called a network policy. And a network policy defines specifically, very specifically, which service can talk to which other service. And it does this by specifying the protocol, the host that it's supposed to be communicating with, and the port. And that's it. So it's a specification of how it should communicate with other services. So this would be allowed, that would be allowed, but this would be automatically blocked because there's no policy for it. So this is starting to look a little bit more verbose if you're not used to looking at Kubernetes stuff. But this is how it all looks like, so get used to it. But it's defined quite simply. The type of this resource is network policy. And we're defining what this network policy, what service this network policy should be used upon. And we're matching upon a label called shipping. So this is only going to apply to anything that has a service name of shipping. And then we've got an ingress and also an egress if you're interested in that, but an ingress specified for from a particular service, so from another service, and then we're specifying it's TCP on port 80. So here we're saying that the service shipping is allowed ingress from orders on port 80, and that's it. Anything out of that range, anything not, a different service, a different port,
it'll be blocked. So let's give that a quick go, because I think that's quite cool to show. So I'm going to SSH into, where is it? So I'm going to SSH into my staging cluster now, if the internet allows. It does, hooray. And when we're there, I'm just going to select which pod is this? I'm going to select the catalog pod, and I'm going to exec into that pod. Okay, and we're in. So let's just go back to that picture again. What we shouldn't really be able to do, but what I'm about to show you, is a catalog connecting to another service. So we're inside the catalog service at the moment, and I'm going to use Telnet because it's just installed by default. Carts on port 80, and then get carts. I know the API, so that's okay. There you go. So I've got some data back. I've got some information about this user's cart when I shouldn't really be able to. So if anybody had access to that, for nefarious means, then they would have access to all of the other stuff as well. So what we can do now is apply one of these example network policies that I just talked about. So let's just go ahead and do that. Okay, that's fine. Again, so these are all defined in the repo that I talked about earlier. We've got lots of these policies for all the different services. And now, if we connect back into the catalog service again, do our telnet again. Yeah, and what was it? Get carts 134 HTTP 1.0. And there we go. So it will just sit there and hang and eventually time out if you want to watch paint dry. It would, I promise you, it would do that. But basically what's happening here is we don't have a policy now between the catalog and the carts service. So it's as if it's not even connected on the same network. And this is all powered by one thing and one thing only. This is only possible because we are using a software-defined network on Kubernetes. So this isn't something that comes standard with your networking stack or the kernel or anything like that. These are all things that are provided by something that's called the CNI interface, the Container Network Interface. It's like an API, a standard API, that all of the software-defined networks adhere to. So basically, you plug in this software-defined network into Kubernetes, and then you get all these features for free. So that's only sort of one small part of it. There's lots of other features of the software-defined networks, like encryption and routing and things like that are all very cool, but we don't have time to look into. But yeah, I think that network policy is probably one of the best use cases for software-defined networks, to be honest, because it's so easy to make a really secure network, which is all software-defined. Okay, so let's start wrapping up. So we talked about some container level stuff. So if you're writing containers, always set a user. If you don't set a user, if anybody has access to that, then you'll be able to, connect to the root file system as well. If you can, make your container immutable. If you make it immutable, then the person that has access to that container can't mess around with any of your files. If you provide restraint to that container and on top of that container, then not only the application, but anybody that has access to that application also cannot do various nasty things that you wouldn't want them to. So just those three things, if you implement those three things, that's it's far stronger than it was in the past, and would probably stop a fair number of attacks just by default. When we're talking about networking, then consider the firewalls basically, but not just a firewall, different granularities of firewalls. If you're blocking and preventing people from accessing your service, then do it at all levels basically. If somebody happens to get through one of those perimeter defenses, then you've got another one to rely on. So global firewall, a Trump firewall, everyone uses Trump firewalls, big S better. Network segmentation for within the application, but then network policy is really key. I think that's one of the coolest use cases there. If you want to try any of these out, you can. So go to git.io/sockshop or just search for microservices demo, and it'll come up with a repo. You can run it locally on your laptop with Docker Compose or Minikube or Mini-Mesos or anything like that, or you can run it on clusters if you like as well. So yeah, check it out, star it if you like it, contribute if you really want to. And if you need any help on anything else, then just get in touch with me. You find my details there, windoresearch.com. And that's it for me. Thank you very much.